Welcome back. So, in the last few lectures, you have learned what are industrial robots. You have got a glimpse of various types of robot when I discussed the classification of industrial robots in my last lecture. So, in today's class, I'll cover two broad classification of industrial robot, which are popularly known as serial robot and parallel robot. Okay, so let us begin. So yes, in today's lecture, I'll be covering serial robots, Cartesian and joint space motion capabilities I'll show you. We'll discuss parallel robots also. I'll introduce you to this special kind of robot, its historical comparison, Cartesian motion capabilities, advantages, disadvantages, and their application. Why this special discussion is required? Because this two kind of robots are most widely seen in the industry shop floor. So most of the applications which are there in the industry, which are made by robots, are by these kinds of robots. Okay, so yes, let us begin with serial robot first. So before we begin, let me just start a small video that will run parallelly while I'll be discussing serial robots. So let us start the Cartesian motion first. So yes, so it is most widely used class of this robot. Okay, so it can make almost all kinds of motion. It can make motion in Cartesian space. Cartesian space is the motion. You see, this robot is moving with respect to its own base frame, about which it is attached to the ground. Okay, so that is the frame. Along different Cartesian directions of that frame, now this robot is moving, you see, moving along x, that is normally I would represent by red. Along y I'll represent along green axis, and along z it is blue axis, if you can see. So yes, all the three directions, you see, translational motion this robot is now making. Okay, and it can also make motion, rotary motion along those axes as well. So you see, it has all the 6 degrees of freedom of in space the end effector can go. Okay, so any object it can manipulate in those directions. Okay, so this is the most widely used class of the robot. So if you go to any industry, all the pick and place task, pelletizing task, welding task, so it is a very powerful robot, and it is almost like omnipresence in the industry shop floor. So yes, and why? Because this robot you can clearly visualize by which direction it will go. If you have to program this robot, it is very easy to visualize the end effector. You can simply jog. They have a teach pendant attached. You have seen in the anatomy class also that yes, there are something which is known as teach pendant. So with teach pendant you can directly jog them in Cartesian space along x, along y, along z, and you can clearly visualize its motion. You can estimate the motion. You can teach this robot quite easily. Okay, you taking it to various places in the workspace. So, and they are very simply constructed. All the joints are very much analogous to the kind of joints we have, kinds of link we have. So even our arm, you see, it is of similar kind. You have a link, you have a joint, you have a link, you have a joint, and finally you have an end effector, that is our palm with some fingers. Okay, so we can hold something and we can orient it in 3 direction. We can move along all the 3 direction. So you see, it is very much similar to our own arm. So we are a kind of brought up with this kinds of arms. Okay, so it is very intuitive to handle this kind of robot. Okay, so and it has, you see, you can handle something which is very far beyond by stretching your arms. Okay, you can hold something, and you can hold powerfully at the center region, and you can handle something. So you see, it has a very good balance between its reach. Okay, you can reach quite far, and you can handle very heavy payload if you are in something around near about to your body. Okay, so then you can handle huge payload also. So yes, That is the beauty of this kind of robot. It has very good balance. Okay, that is what is making it very much omnipresence in the industry. Now it is making rotary motion. You see, it is rotating up its end effector frame about the y-axis. Okay, that is the green one. Got it? And similarly, it has made rotation about. So now it is moving, rotating about z-axis. You see, it is making almost all kinds of motion which are required normally to handle any object. That is, all 6 degrees of freedom motion is possible, at least with this robot. So not all robots which are serial can be of this capability. This is a 6 degree of freedom robot. You now understand already. So yes. So these facilitate, this type of motion can facilitate any kind of pick and place motion, a point to point trajectory. It can take you from a point and bring it to other program point. Not just the point where I mean is a point in space. It is position and orientation in space to a position and orientation in space. So it can gradually make itself grow from one pose to the other pose. Okay, so pick and place task mostly requires this kind of motion. So now we commonly call it as PTP motion. Okay, it can be a combination of primitive tasks. So industrial robot controllers are pre-built with some kind of motion which are like circular arc. They can be defined in different ways. Can be defined like 2 points and a center point, or radius and 2 points in the space, or maybe just 3 points in the space. That is easy to define a circle also. So there are various ways you can make your robot go in circular way. Your end effector will go in a circular trajectory, and similarly line in space can be defined by any 2 point in the space. So that those are few standard motions that this kind of robot supports. Okay, and it can also do interpolated spline trajectory, which are mostly common when we do painting job or a welding job, a gluing task or a laser cutting. You have already seen various such kinds of motion where you require a robot to move in a free form shape in the space. Okay, so that can be programmed. So again, when we program, I don't just mean it can go point to point only in position. It will continuously gradually shift its orientation, which was taught at every location in the workspace. So that is how it can be programmed. So this kind of programming is already fitted into this kind of robots controller. Okay, so yes, and the compliant motion task, it can also do compliant motion task. Not all robots can do compliant motion. There are special kinds of robots which are known as collaborative robots or cobots, so which are joint compliant. So their joints are not very stiff, and you can make it go backward also. That means they are all back drivable. They are gravity compensated. So they have many other. They can be controlled for impedance. They can be controlled for stiffnesses at its joints, even at its end effector level. So those kinds of robots are soft robots, and they are compliant. So using force torque sensors, it is made so. Okay, so that is also possible with this kind of robot. So yes, there are many other capabilities this robots can see. So the next one is a joint motion capability. So first you just see this axis 1 is moving, and it is making it go in a circular arc in space. Okay, again I'll make second joint to move. Yes, the second joint is moving, and again it is going in a circular arc. Okay, now I'll make third joint move. This is the third joint. Now I am moving. See, again it is in a circular arc. So from the axis of rotation, you have a center, and then end effector goes in a circular arc. So this type of motion is known as a joint space motion trajectory, in which a robot is made to move about its joint only. So one of the joint or a combination of joint is made to move. Okay, and then you can take your robot to go to a particular place. In this, we are not very specific to move in spatial trajectories like linear displacement along any of the axis or rotary along any of the axis. Okay, so each joint could create a segment of circular arc in space. Okay, and but it is very difficult to estimate the robot's tool path. This is a complex robot with multiple links connected one after the other. So while moving one of the joint, you cannot estimate precisely where your robot will go. Whereas when you were moving this robot in Cartesian space, what you saw, it will go down along z-axis. If you are just jogging it along negative z-axis, you can clearly understand, yes, it will go down. But in this case, you cannot predict where this robot will go. Yes, you have some estimate that yes, it is going to make some circular trajectory in space, but using this kind of trajectory for programming is not at all advisable, because it is very difficult to estimate the tool path. Yes, very experienced users can do it. So it requires proficiency in robot programming skill if at all you want to use it. So you should be very much familiar with this robot. And configuring axis specific workspace also is there. So the way you could confine your workspace in Cartesian Cartesian motion of this robot. Let's say you don't want your robot to go to a particular workspace, so you can definitely put that workspace out of the programming. Okay, so there are provisions in robot teach pendant where you can define x min, x max, minimum and maximum values of x. Similarly, minimum and maximum along y, minimum and maximum along z also. Okay, so that is what you can mention, and you can clearly say, okay, this is the cube within which I want to work, or this is the cube within which I don't want to go. Same way, when you are programming for axis specific motion, you can also limit your joint motions, and your robot will not go to a particular joint segment of your robot. Okay, so whole of the rest of the space your robot joint will move, whereas it will simply exclude that space from while it is moving. Okay, or it can do otherwise also. It will go work only in that space, and it won't work in the spaces which are not in that. Okay, so that is what is also possible. So yes, and then this restricts the robots entering into possible areas of collision. So this is done in order to avoid collision with surrounding objects. You have an object in that particular location, so that is the reason why you should do this. Okay, so yes, it is also applicable for Cartesian motion that I have just said, something that I am doing for joint space. Similar analogy is there in Cartesian space also. Okay, so programming for path that passes near to the robot's singularity. This is very much to be understood first. So I'll show you in kinematics why a robot is singular. Okay, so those are the places where you should avoid robot going, because that is the place when it is mathematically singular and you don't have solution to get the joint velocity corresponding to any Cartesian velocity. Okay, so there is no relation that exists in, at least in those places. So going near to singular will make your robot move at, let's say, very high velocity in those cases, and your motor will draw a huge amount of current for that reason. So your robot may just trip at high current in that cases. Okay, so you should avoid going to those places. So clear understanding of this I'll be giving when I'll be discussing singularity in robot kinematics. That is the Jacobian relation, that is the relation between velocities of end effector and the joint motions. So programming a robot to go near to robot singularity is tough task when actually you do robot programming in Cartesian space. You don't know if you have made it go from point to point. There may be a point in between through which your robot cannot go. Maybe it is a singular pace. So in those cases, you have to use joint motion capability. So that is the place when we normally program the robot to move just the joint and still pass through the same workspace or same point. Okay, so that is quite possible if you program your robot to go through the joint trajectories. Okay, so now let me introduce you to parallel robot. What are the capabilities? What are the applications? Okay, so yes, lawn tennis is a fantastic game. So you just see what this player is doing. So it is she is stretching her arms. Okay, she has a link and a joint, a link and a joint, and you see at the end she is holding a racket and playing lawn tennis, right? So that becomes her end effector, in which she is holding a tool and handling, manipulating an object which is floating in space. That is a ball. Okay, so hitting a ball requires all six-dimensional motion. She needs to orient her bat and as well as locate her bat anywhere in space. Okay, so yes, forget about the additional motion that the whole of the body can do. At least just by the arm, like a table tennis also, one can make such motion. Okay, so yes, this is one motion which looks like a serial arm. So yes, so what difference you see here now? Now she is attempting to play a ball which is very closer to her body, and maybe she needs a huge amount of power to do that. What now she is doing, she is holding her bat with both of her arms. Okay. So what is the difference now? Okay. So just pause for a moment and think, what was this and what is this? So that was a fully stressed arm, that is a serial arm. So this kind of motion, when you are holding two serial arms together and creating a end effector, some manipulation task. You also have an end effector over here with a tool, that is your palms, combination of palms that acts like a gripper, in which you can hold a tool and do something. Okay, so this kind of motion is known as a parallel kind of motion. So in case of robot terminology, we call it a parallel robot. So yes, so this is your serial robot. This again is a fixed base robot. It is mounted at base, founded to the ground. You have a joint, you have another joint and a link, a joint and a link. You have multiple joints and a link. Finally, you reach to the end effector frame. Okay. So yes. So this is a robot. It looks like a manipulator or a platform. Yes, it is very, very similar to that. The way the robot is defined, a manipulator can be a robot if it fits well in all those definitions. So yes, these are actuators. You see, it has one linear actuator that can make this kind of motion. It has another linear actuator, yet another one, you have another one. So these are nothing but, this is a Stewart Gog platform. Okay, so it has 6 linear actuators that connects the bottom platform using a spherical joint here and maybe a universal joint here, or it can go otherwise. So it is universal here, prismatic here and spherical here. So it is known as 6UPS robot. Okay, or a Gog Stewart platform. So this is a parallel robot. You see, all the 6 actuators are simultaneously moving the top platform to achieve any kind of motion. So these robots, yes, they have limited workspace, but they are very, very powerful. Okay, to make any kind of motion, all the arms, those are the actuators also, are moving simultaneously using their power to do that. Okay. So yes, and you have all the actuators itself that becomes the links. Okay, so we don't have any additional link here. Okay, so that is the reason probably these robots are also maybe a little lighter as compared to similar powered serial robot. So we'll see a brief comparison now. So yes, you have already seen the video for serial robot now, making it go in Cartesian workspace as well as a joint workspace. Now, yes, I'll show you some videos for parallel one also. Okay, so let us discuss the brief history of parallel robot now. So you see, this is the first platform which came in that was reported, that is in 1928, okay, which was known as oxymoron, okay, which was a motion based platform patented by James. So you see, it has a, that was nothing but a spherical parallel robot near to the, you see, this patent was filed almost near to the first motion picture which came in similar year, okay, and it is so age old, you know. So even serial robot is reported quite early in those days. So yes, and no reporting on any hardware being developed on that, okay. So after this patent there was no hardware which actually came in, okay, and because you see this parallel robot is very complex, the mathematics is complex, computing the workspace is very complex, estimating where it will go by moving just one joint, it is very difficult to visualize, okay. So industry was not ready to handle this complexity mathematically, as well as the kind of computational power that we had due to the kind of computers that existed in those days was not that good, okay. So yes, this invention was on hold quite long time till we see actual computers which can handle this mathematics came in, okay. So yes, in 1934 Pollard came in with a new patent for a spray painting parallel manipulator. Unfortunately, again, no machine was ever built for that. Patent was filed which claims that it can do some spray painting operation using parallel manipulator, but no machine was built. So this was in 1934. And then in 1954, you remember, this is just 1 year near to the serial robot discovery, okay. So serial robot patent, okay. So Dr. Eric Gogg came up, he was an automobile engineer at Dunlop Rubber Company at Birmingham, okay. So he built the first hexapod, that was the first machine which was built on parallel architecture, okay. That was used to test the tire which they were manufacturing, okay. So yes, in 1965, Mr. Stewart, he came in. He described the 6th degree of freedom flight simulator. Okay, so he followed by chain of publication by Mr. Stewart. So yes, after his coming in 1965, he could publish a series of paper based on parallel architecture. Okay, so this men, Eric Gogg and Stewart, were the pioneers in this. Okay, so in 1954, George Dayal, he applied for the first industrial robot arm patent in 1961. So you see the years are very close, 1954 and 1954. You see this parallel robot, because of its complexity, it was on hold. The kind of mathematics, the kind of technical reportings which were there in those days, it went little slower for parallel robot. Although the applications you will find, even parallel robots are most widely used nowadays. Okay, so the first industrial robot was built by Unimation. This is just for the comparison. I have just noted it here so as to compare the years. You see, both were patented in almost similar year, and both the discovery started almost in the same time, but whole of the development and seeing this platform in industry software went at different speeds. Okay, so yes, so now parallel robot Cartesian motion capability I'll show you. So yes, you see this robot, this is a 6th degree of freedom robot. You see there are 6 actuators, all simultaneously they are moving, all are rotary joints. So one end can have a spherical joint, other one can have universal joint, but in this case it is both spherical rod and bearings, so it may be called as 6 RS. So that is 6 revolute spherical joint. This again is a 6 degrees of freedom robot. You see, it has made a translation motion along all the 3 Cartesian direction with respect to its base, and you see this is the third one. So again, it can do all kinds of rotary motion also about each of the axis. So you see, this is fully capable. The way your serial robot was moving, this also can move. Most popular variant in industry is the 3-DOF delta variant, okay, that you have seen in the kinds of robot that we have discussed in classification. This can do pick and place task also. This normal configuration in which this can do pick and place is mounting this inverted, okay, and you can put your end effector at the tip platform, okay, and you can make it have a gripper and do some pick and place task also. These are very commonly used for 3D printing, okay, in medical surgery when you need your end effector to be very stable and very precise and stiff, okay. So these are a few applications, you see. So the configuration which is shown here is a 6 degrees of freedom parallel robot in 6 RSS Jamanov configuration, okay. So these robots, you see, all the 6 actuators are moving simultaneously. There are no actuators which are mounted on the link. Your links can go very light in this case, right? So that makes whole of the structure very light. So that is the reason it is very fast, and that is the reason it doesn't have much of an inertia also as compared to serial robots. So they are very precise also. So the fastest robot which are reported are parallel robots. So it has very good power to weight ratio. Okay, so but they are very complex. You see, they are complex. Solving for mathematics of this is not that trivial. So high-end controllers are required, okay, because of its perplexed kinematics, dynamic solution, workspace singularities exist. So it doesn't just have singularities at its boundaries, it also has singularity within the workspace. So finding out those singularity position is again a challenge. All the capabilities what a serial robot has, this also has, okay, but you see it has limited workspace. So only limitation what it has is its small workspace, okay. But the joint motion planning is far too complex. You cannot estimate where your end effector will go. It is even complex as compared to your serial robot. So just moving one of the joint can make an arbitrary motion in the space that you cannot predict, okay. So even a very good programmer cannot understand that. So joint programming in this case is just excluded, okay. You cannot do that. It is far too complex to be used by any expert programmer also, okay. So yes, let me just discuss some of the applications of these robots in the industry. So you see, flight simulators or a naval simulator, mining or truck simulator, so where you can train the drivers who will actually drive the real vehicle. So this is just the cockpit of the flight which is placed on top of a parallel platform. So this looks like a Stewart Gog platform only. So you have a bottom base which is attached to the ground. You have a top platform which can make motion, okay. So on top of that you have a cockpit. So a person can sit within this cockpit, and this platform, based on the graphics that is shown in front of the driver, okay, he also sees the motion, okay, so that he can get complete immersive feeling of the actual environment that he is going to face when he will be riding upon a real flight. So that is what is simulator, okay. So yes, it is used for that reason. And moving giant telescopes. So telescopes require very precise location of this top sensors, okay. So that is to be located very precisely, that is to be oriented very precisely, because even having an error of fraction degree over here can have huge displacement when it actually sees any object in space because of the distance. So that is the reason it requires very stiff base and very precise end effector. Okay, so that is the reason for mounting any giant telescopes or even solar panels, you use normally parallel platforms are used. Okay, pick and place task in any industry. You see, this is a standard delta robot which is picking a moving object from a conveyor. Okay, so that is most common in food packaging industry, agro industry. Mainly 3DOF delta variant is popular in industry, which has only 3 translational degrees of freedom, can just pick and place. Okay, in medical robot for surgery it is used. So you have all the 6 actuators, those are here. So this is not the only one. There are even many other industrial robots which uses this. Okay, even your Da Vinci robot that you have seen in the classification, that also uses a kind of parallel architecture at the end. It has a serial to expand its reach. Okay, and it ends with a parallel architecture at the end. So it is a serial parallel system. Okay, so this is just a parallel tip which is holding a kind of needle over here. Yes, so now you can see the needle also which is here. So this is the needle which is mounted here. This is the top platform. This robot is mounted inverted. Okay, so this is an application which is using a parallel robot in the medical surgery. So it can be a laparoscopy tool also. So again, it is used for 3D printing. This is one of the most popular variant of 3D printer, in which you have all the 3 linear actuators which are mounted like this. It has 3 linear actuators. Okay, that can take these links. These are the links simultaneously go up and down while it builds up this object in 3D. Okay, so as it is builded layer over the layer, so this all the 3 links can go up, and it can, by adjusting the lengths of all the 3 links, L1, L2 and L3, these 3 links which can extend and retract, so those are prismatic joints basically. So that is attaching this permanent links. Okay, and making it go anywhere in this region. So it can make XY motion like this anywhere, and it can go up and down. It is a 3 degree of freedom robot. So you also have a parallel robot for 5D milling or 5D printing also, which works in a similar manner. You have a micro manipulator to do any kind of, let's say, brain surgery, or so this is just a mock which I got from one of the literatures available over internet. So yes, you see this is a parallel steward platform which is mounted with a needle that is working somewhere in the brain part of our body. So yes, this is your micro manipulator kind of thing. So not just for this, it can be used for, let's say, assembling your wrist watches. Okay, so that can be handled also. So most of the applications where a serial robot can go, with some exemptions, even parallel robot can go. Okay, so workspace can be very similar. Only limitation is in reach. Okay, otherwise it can do everything. So this is the Da Vinci robot, which has a serial arm with a parallel end which goes over here. Okay, so this is what I was talking about when I was telling about medical robots. So this is the robot. So yes, there are many advantages of parallel robot. You see it because it is mounted on top of all the 6 actuators which are very stiff. So they are very stiff. That means you don't see much of a jerk due to external load variations. Okay, so it has very high stiffness. Load is shared by multiple legs. It has very high accuracy also as compared to serial robots. When you have a joint, if at all you have an error over any of the joint, it is felt at the top. So all the joint errors are accumulated together, and you can see at the top it has huge amount of error that can go. So in this case, you have all the actuators basically which are connecting the bottom and the top frame. So any error in one of the joint may be compensated by the other one. Okay, it need not necessary that they are being added together. Okay, so that is the reason they are very, very accurate. Joint manufacturing or the assembly errors will even out rather than getting accumulated at the end effector, as in case of serial robots. Okay, so it has very high speed motion. You see, their links are the actuator itself, and you don't have any actuator which is mounted on top of the link. So your links are very, very light, so that is making it a very low moment of inertia. So that is the reason why your links can move at very high speed. So effectively whole of the robot can go at very high speed. Okay, so high payload to self weight, because your links are lighter, whole of the robot is lighter for the same payload capacity. So it has a parallel robot has got very good payload to self weight ratio. Okay, and high natural frequency. Why this is fruitful? Because you see, they are very, very stiff. So that is the reason natural frequencies goes very high. So in case of serial robot, if it is very, very long, it may match with the working environment frequencies, and that can resonate with the system. So that cannot happen with this. If your frequency goes very, very high, natural working of your robot cannot match with the frequency of your cycle operation. Okay, so this is very, very fruitful. So you can work at very high speed also without getting worried about whether it will match with your working cycle or not, whether it will match with your natural frequency of the robot. Okay, so that is the reason it is very, very useful, and you don't have any control in case of serial robot, even if it happens that. So you just have to skip that working frequency, working cycle. Okay, that cycle frequency you have to just exclude from your programming system. Okay, so it has, again you see, high power to weight ratio. So it draws very less power for the same payload capacity robot as compared to serial robot. It is different from payload to self weight ratio. Okay, so yes, you have already seen it has limited workspace, but it is not an issue if you plan your workspace properly. Okay, you mount your robot in proper location, you can very well create a very good workspace. Sometimes it is preferable to put this robot inverted and you have huge free space at its bottom. Okay, at the base you see it has a free space where you can manipulate its end effector. Okay, so that free space is there. Okay, so that is not much of an issue here. Singularities, it is also there in case of serial robot. Only thing, if you know it, it is very good. Okay, you just have to find it out. That itself is a problem in case of a parallel robot, but at least with delta it is very well known where are the singularities, and you can easily avoid that. And mostly in industrial robots, they work on PTP base, that is point to point programming, in which you record a joint position and just replay that joint positions. Okay, in order to do any pick and place tasks. As because delta robot kind of parallel architecture, which is very, very popular in the industry, they are basically using delta robot, and it doesn't face any singularity because it works in joint space, not in Cartesian space. It doesn't have to relate the end effector motion to its joint motion. Okay, so Jacobian getting singular is totally absent. We'll discuss more about this when we'll be discussing singularities and differential motions. Okay, so yes, they are non-linear. Even serial robots are non-linear, so even that is not much of an issue. Okay, so yes, you have now seen the power of parallel robot also. You already know serial robots, they are very, very popular in the industry. So with this, I'll end today. In the next module, we'll start with actuators. Actuators gives powers to the joint, different kinds of actuator. Mostly we'll focus on electrical actuators. Okay, so that's all for today. Thanks a lot.